Okay, let's get started. This is the first seminar session, and as I promised, sometimes we may have topics which belong to the core dynamic programming framework, but for one reason or another, they are not covered by the Stokey-Lucas textbook, and the Howard policy improvement or iteration algorithm is such a topic. It is described in the Ljungqvist-Sargent textbook, Recursive Macroeconomic Theory, on page 114. Both the algorithm and the description are very effective, and it is easy to learn. So let's have a look at the algorithm through an example in a context. The context is the Brock-Mirman stochastic growth model, in which the problem is the maximization of lifetime utility coming from consumption. As you can see, we have a transition equation in which the next period's capital stock is the difference between current period output and consumption. Output in period t comes from a production function, which is the usual diminishing marginal product production function with a positive technology parameter a. There is only one input, capital, and there is a stochastic, with the normal distribution, a stochastic shock. Its distribution is known to agents, so they can form rational expectations. So agents are supposed to find an optimal plan or optimal path for the capital stock and consumption. They are the same on the basis of the initial capital stock and their expectations regarding the stochastic process. Okay, so this is the problem. The algorithm consists of a few simple steps. First, we guess a policy function in the 1-0 interval. So simply it means that based on this policy rule, we save a certain share of period t output as next period's capital stock. We don't know if this policy rule we just guessed is optimal or not. Probably it isn't. It is just a guess. It's not supposed to be optimal. It is just a guess, by which in the second step we expand the value function. So on the basis of this H0 policy rule, we calculate the value of lifetime consumption of the agent who uses this policy rule. At the end of this step 2, we will have a closed form, in this case a closed form value function. This is J0. Step 3, find the new rule H1 by solving the value function problem. It is the related value function problem, in which this is a simple Bellman equation in which we try to find the optimum capital stock for next period on the basis of the value function from the previous step. So the only thing we need to realize is it is the same value function iteration process on the basis of policy functions. So we maximize this Bellman equation, and in the end we will have another policy rule H1, and we will repeat these steps until convergence applies with respect to the policies. This is a very simple algorithm. so it can be repeated for good, but we don't need to repeat too long, because this algorithm produces the optimal policy in one single step. So after one round of iteration, we will have the final and optimal policy rule. Let's apply this policy improvement algorithm in the context of the simple cake eating problem. Alright, so let's see the basic cake eating problem in the Howard policy iteration algorithm. The problem is familiar. We want to find a consumption path that maximizes the agent's lifetime utility, supposing that this transition equation applies and supposing that the initial size of the cake is given. First, we guess a policy rule. It's not supposed to be the final rule, it's only an initial guess that describes how next period's cake comes from today's cake size. And on the basis of this simple policy rule, ad hoc policy rule, we want to describe in a closed form this value function. I would say we want to solve this value function problem, but actually we assume a policy rule, so it's not about solving this value function. Rather, we just want to describe a closed form result. That's all. So first step one, we need a recursive formula. To describe cake dynamics on the basis of this ad hoc policy rule. We know that this is true. It is also true so it's no big deal to find a general equation, formula, this is the recursive formula we were looking for to describe how cake size changes in time. Step 2, we try to find a closed form solution, air quote, for the value function problem. I'm emphasizing again that this is not a solution because we have the not the solution but a guess on the basis of which we are trying to describe the value function. This is the value function on the basis of policy rule H0. So let's start expanding the value function. This is the problem. We have a simple logarithmic utility function, and actually this is in another form our problem. Okay, I'm doing nothing but using the formula we have. I think we have one more line. Yeah. Okay. This is a great start. So here we go. Let's start expanding. So in the first period we have this line. I promise I write down only the first few cases. I know this is lame, but I'm trying to be as accurate as I can. Okay, expanding. This is all we do here. Soon we will start using the recursive formula. One more. Okay, and I think it's more than enough. It's more than enough. Okay. Now we will use the simple recursive formula, which I'm writing down just for emphasis. So on this basis we are going on. And so on. And the second part of the equation, this long equation, I know it may look horrible, but you will see it's gonna be very simple. So luckily there are patterns to realize in this equation, and for the first sight it's obvious that there is a first part of the equation and there is a second part of the equation which can be divided into two parts, and I will show you how right away. As far as the first part of the sum is considered, it's simply simple infinite sum. Okay, that's nice. And the second part is this part. Oh geez. there is a pattern to realize. We are using the recursive formula, so we are making good use of it. I hope it's correct. And so on. So, as I promised, it can be divided into two parts. One is a simple infinite sum. Actually, the other is also an infinite sum, but a bit complicated, more complicated. So it's simple. Yeah, I think it's correct. And 2b, let me rewrite for emphasis. Because it's gonna be helpful to have the equation in a distinct line. Yes. And expanding this part of the sum, we will see that it is the infinite sum of infinite sums. Now you can see we have two pieces of this part of the sum. So simply we have another copy of this part of the equation. We have two. So we are done with this part of the equation. Here we have three parts of the equation. And we have all three. And here we have four. So here we go. And it goes to infinity. These sums can be described in a more condensed form. This is the first. This is the first. Sorry. This is another infinite sum.
plus. This is done. And so on. So this was the fourth part of the sum, and it goes to infinity. So in the end, it turns out that the sum can be rewritten in an even more condensed form. I think this is beautiful. And I promise it's gonna be the end result. Okay, so we are done with this part, and on this basis now we have a full description of the value function based on the rule age 0 we guessed in the very beginning. So once again, we just guessed a policy rule that made sense. Yeah. Okay, it's not too nice, but if you give me a second, I'm just switching the order of the components. I think it's correct. I don't need the ruler. How to switch this off? Go away, please. Yeah, and I'm leaving some space. And it's interesting to realize that this is a constant. This is a constant which is based on the policy rules. It is specific to the policy rule we picked in the very beginning. So in a more condensed, even more condensed form, we can say that on the basis of the policy rule we guessed in the very beginning, we have this value function. Okay, so short answer to the question we posed in the very beginning: given policy rule age 0, this equation describes the value the consumer, the agent, can gain from consuming the cake by following policy rule H0. The next step, step number 3, is to find a new rule. This is gonna be H1. By solving the related functional equation, value function problem. It's not a functional equation. It's just a value function problem where this is CT, consumption. No, let me rewrite this part. So we want to maximize this value function by finding a new rule, right? So this is C0, and this is the point, and this is the previous value function. So this is the point where the new rule will come up. This is a simple maximization problem, so we will have the first order condition. So we will, so our choice variable or control variable is cake size in the next period. So we need to derive this function with respect to W1. And here is the result. Yeah. I think it's correct. -1 over plus, yeah. And in a few simple steps, it turns out that the new rule is beta. And we know it from our previous exercises that this is the optimal rule. This is the optimal rule. So it is really true that Howard policy improvement algorithm leads to the optimal policy in one simple and single step. So we know, okay, let's not go ahead. So what we know, that after one round of iteration we have this policy. Okay, we know that this is the optimal policy, but just because we did the exercises previously, so let's pretend we don't know this rule. So let's try step 4. Let's try to find a better rule. And this is H2. On the basis of this, on the basis of the value function, which is built on this policy rule, we explicitly need this value function. It looks horrible, but luckily we can use the result of the previous step. So we don't need to go back to the recursive formula to rewrite the whole value function. We can use J0 by replacing age 0 with age 1. Okay, so we can save a lot of work by using the previous value function and replace rule age 0 with rule age 1. Sorry. So this is age 1. This is age 1. So we can say, on the basis of this policy rule, we have this value function. So let's try to find the new rule h2. Let's solve the same value function problem. Not 2, 1. And I think in other terms it's correct. We have the first order conditions. The decision variable is W1. So the first order condition looks pretty the same. And in a few simple steps, we realize that there were no further improvements. Once we found beta as the optimal policy rule, no matter how further improvements we try to make, we will receive the same rule again and again. So this is the reason why we say that how our policy improvement algorithm leads to the optimal policy in one single step. That's all.